Hello, my friend. Reality feels obvious because you wake up inside it every day. The room is here, your body is here, time moves forward, and the world behaves as if it has always been solid and complete. But the deeper science goes, the less simple that picture becomes. Tonight, we're going to follow a strange possibility carefully and calmly. Not that reality is fake, but that it may be built on a layer we don't yet understand. If you have trouble falling asleep, then you're in the right place. Let the day fade and let this question open slowly. Chapter 1. The strange question beneath ordinary reality. To ask whether reality could be a simulation is to touch one of the most fundamental and exciting questions a human mind can ask. What is the world we wake into every day, and how do we know it is what it seems? At first, the question may sound like science fiction. It may bring to mind glowing code, artificial worlds, or machines powerful enough to imitate an entire universe. But underneath those images is a much older and quieter question. Long before computers existed, people wondered whether the world of experience was identical to the world as it truly is. They asked whether sight, sound, touch, memory, and even the feeling of being awake could ever give us perfect access to reality itself. The simulation idea is a modern version of that ancient uncertainty. It begins with the simple fact that every experience you have is filtered through a living brain. You do not see the world directly in the way a window lets light pass through unchanged. Light enters your eyes, touches sensitive cells in the retina, and becomes electrical activity. That activity travels through nerves and is processed by the brain. From this process, your mind constructs color, shape, depth, motion, and meaning. The red of a sunset is not floating in the sky as redness itself. It is a pattern of light interpreted by your nervous system. The sound of rain is not carried into awareness as sound already formed. It begins as pressure waves in the air, becomes movement in the ear, then becomes signals the brain organizes into rhythm, texture, and distance. The world you experience is real in the sense that it is caused by something outside your imagination. But the experience itself is a model built inside you. This does not mean reality is fake. It means your access to reality is indirect. The brain is not a passive recorder. It is an active interpreter. It fills gaps, predicts patterns, corrects errors, and builds a stable scene from incomplete information. When you look around a room, you feel as if everything is present all at once. Yet your eyes only see clearly in a small central region. Much of what feels like a complete visual world is assembled from memory, expectation, and quick movements of attention. Your brain is constantly making its best estimate of what is out there, using the evidence available to it. This is why illusions can be so revealing. An illusion is not just a trick, it is a window into the machinery of perception. A still image can appear to move. A shadow can change how bright an object seems. A sound can seem to come from one place when it is actually produced somewhere else. In each case, the brain is not failing randomly. It is applying normal rules that usually help you survive. It assumes light comes from above, that objects remain stable when partly hidden, that nearby signals often belong together, and that familiar patterns are meaningful. Most of the time, these assumptions work beautifully. Sometimes they show us that our experience is a useful construction, not a perfect copy. Dreams make the mystery deeper. In a dream, a whole world can appear without light entering the eyes or sound entering the ears. You may walk through places, speak with people, feel fear, confusion, wonder, or relief. While the dream is happening, it can feel immediate and convincing. Only after waking do you recognize that the world was generated from within. A dream is not the same as waking life, and it does not prove that waking life is artificial. But it shows that the brain can create an immersive reality from patterns of activity alone. It can build a world convincing enough that, for a while, you live inside it. Waking experience is different because it is strongly constrained by the outside world. You can return to the same room and find the same table. Other people can describe the same storm, the same street, the same sky. Scientific instruments can measure regular patterns that do not bend to personal wishes. This shared stability is one reason we trust that there's a real external world. But even then, the world as it appears to us is not the world in its deepest physical form. What feels solid is mostly empty space structured by electromagnetic forces. What feels still is full of microscopic motion. What feels like simple matter is described by fields, particles, probabilities, and interactions far below ordinary perception. The simulation question begins to feel less strange when we notice this gap between appearance and structure. Everyday reality already hides its own foundations. A wooden table seems simple, familiar, and continuous, but physics describes it as a vast arrangement of atoms held together by forces. The atoms themselves are not tiny wooden beads. They are patterns of matter and energy, with electrons existing in states that do not match ordinary pictures. Solidity is not the absence of emptiness. It is resistance created by forces between particles. The table is real, but not in the simple way it appears. It is a surface-level experience of something much deeper. The same is true of time. We feel time as a steady flow, moving from past to future at a constant pace. Yet modern physics shows that time is connected with space, motion, and gravity. Clocks do not always tick at the same rate in every condition. A clock moving very fast or sitting in stronger gravity can measure time differently from another clock. This does not mean time is imaginary. It means our everyday feeling of time is only one limited perspective on a deeper physical structure. So when we ask whether reality could be a simulation, we are not simply asking whether the universe is like a computer game. That comparison can be useful, but it can also be misleading. A simulation, in the broadest sense, is a system in which one set of rules produces the appearance of another world. A simulation does not have to contain the thing itself. It has to contain patterns that reproduce some behavior of that thing. If an advanced civilization, or some unknown process beyond our current understanding, could produce conscious experience inside a structured system, then the question becomes not just technological, but philosophical and scientific. What would count as real from inside such a system? This is where the idea becomes difficult. If a simulated person feels warmth, remembers childhood, studies the stars, and cares about others, are those experiences unreal simply because their foundation is different from what they assume? We usually call something real if it has consistent effects, if it can be shared, if it follows stable rules, and if it matters to the beings inside it. By that standard, even a simulated world could be real to its inhabitants. It might not be fundamental reality, but it would still be experienced reality. This distinction is important. The question is not only whether our world is real or false. It may be whether reality has layers. Science is careful with such questions because a useful scientific idea must connect to evidence. It must help explain observations, make predictions, or at least suggest ways the world could be tested. The simulation hypothesis is fascinating, but it is not yet a confirmed scientific theory. We do not have clear evidence that the universe is artificial. We do not have a known signal of hidden programmers, cosmic code, or deliberate design. Many versions of the idea may be impossible to test, which makes them closer to philosophy than physics. That does not make the question worthless. It simply means we must hold it gently, without turning mystery into certainty. There are, however, scientific reasons why the idea attracts serious curiosity. The universe behaves according to mathematical rules. Physical systems can be described in terms of information. There appear to be limits to how much information can fit in a region of space. Black holes connect gravity, entropy, and information in ways that still challenge our deepest theories. Quantum physics suggests that the state of a system is not always a simple list of definite properties waiting to be revealed. These facts do not prove simulation, but they make reality seem less like a collection of solid objects and more like a structured pattern governed by rules. Still, we should be careful not to confuse mystery with evidence. A strange universe is not automatically a simulated universe. Quantum uncertainty is not proof of hidden code. Mathematical order is not proof of design. The limits of human understanding are not gaps that any idea can fill. Good science moves slowly. It asks what is known, what is unknown, and what would change our mind. The simulation hypothesis remains a possibility to think about, not a conclusion to accept. Its value may be less in giving an answer and more in sharpening the question. What would reality have to be for experience like ours to exist at all? That question brings us back to ordinary life. You are sitting somewhere, listening, breathing, noticing words unfold in time. The room around you feels stable. Your body feels present. The day may have been busy, bright, heavy, or full of unfinished thoughts. And yet, beneath everything familiar, there is this quiet mystery. Experience is happening. A universe, whatever its deepest nature, has produced awareness from which it can be wondered about. Maybe reality is fundamental. Maybe it is emergent from deeper laws. Maybe it is information arranged in ways we do not yet understand. Maybe the simulation idea is only a mirror, reflecting how little we know about consciousness, matter, and time. For now, it is enough to begin with humility. We do not need to force an answer too soon. We can let the question open slowly, and as the day loosens its hold, you can rest in that uncertainty without needing to solve it tonight. Whatever reality is at its deepest level, this moment is here softly, carrying you forward, one quiet breath at a time. Chapter 2. How the brain builds the world you experience. Every moment of your life feels as if it opens directly onto the outside world. Yet what you actually live inside is a carefully built interpretation created by the brain. This interpretation is not a weakness or a flaw. It is one of the most remarkable achievements of the nervous system. The brain sits in darkness, sealed inside the skull. It never directly touches the trees, the sky, the face of another person, or the room around you. It receives signals. Some arrive from the eyes, some from the ears, some from the skin, some from muscles and joints from deep inside the body. From all of these streams, the brain constructs a world that feels continuous, stable, colorful, meaningful, and present. It gives you not only sights and sounds, but distance, direction, texture, balance, emotion, and a sense of being located somewhere. This process begins with sensation, but sensation alone is not experience. The eyes receive patterns of light, but light does not arrive already labeled as a chair, a window, or a human face. The ears receive vibrations, but vibrations do not come with built-in meanings, such as footsteps, music, or rain. The skin receives pressure, temperature, and chemical signals, but those signals do not announce themselves as a soft blanket or a cold glass. Meaning is added by the brain. It compares incoming information with memory, expectation, context, and the needs of the body. What you experience is the result of this constant conversation between the world outside and the nervous system inside. One of the most important things the brain does is prediction. It does not wait passively for information and then assemble reality piece by piece. It is always guessing what is most likely to be happening, then checking those guesses against incoming signals. This is why the world feels smooth, even though sensory information is incomplete. When you walk through a familiar room in dim light, you do not need to examine every object carefully. The brain uses what it already knows. It expects the floor to continue under your feet, the walls to remain where they were, and the door to be in its usual place. These expectations are not fantasies. They are useful models, shaped by past experience and constantly corrected when new evidence arrives. Vision gives a clear example of this hidden construction. The image falling on the retina is flat, upside down in optical terms, and broken by blind spots where nerves leave the eye. Yet you do not experience a flat patchwork with holes. You experience a three-dimensional world. The brain estimates depth from many clues. The difference between the images in the two eyes, the way objects overlap, the way light and shadow fall, the way textures shrink with distance, and the way motion changes as you move your head. None of these clues alone is perfect. Together, they allow the brain to create a convincing sense of space. Color is also a construction. The physical world contains light with different wavelengths, but color as you experience it is produced by the nervous system. The same object may reflect different mixtures of light at sunrise, at noon, or under an indoor lamp, yet you still recognize it as having roughly the same color. The brain performs a kind of correction, comparing surfaces and lighting conditions so that the world does not seem to change wildly every time illumination changes. This is why color can be stable enough to guide daily life, yet flexible enough to be fooled by unusual lighting or carefully designed images. Hearing is built in a similar way. Sound begins as waves of pressure moving through air. The ear transforms those waves into patterns of neural activity, but the brain must still decide what caused them. It separates speech from background noise, groups notes into melody, locates a sound in space, and recognizes the emotional tone of a voice. When someone speaks in a crowded room, your brain can focus on one voice and soften the rest. This is not because the other sounds vanish. It is because attention changes, which signals are emphasized. Experience is not just what enters the senses. It is also what the brain decides is important. Touch may seem more direct because it is tied to the body itself. Yet touch is also interpreted. The brain combines signals from the skin with information from muscles, joints, and movement. This is how you know where your hand is, even with your eyes closed. It is also how you can feel an object through a tool, as when a cane, brush, or spoon seems to extend the reach of the body. The brain can temporarily include external objects in its body model when they provide reliable information. Your sense of the body is therefore not just a fixed map, it is a living system, constantly updated by action and feedback. The body itself plays a deep role in shaping reality. The brain is always monitoring hunger, thirst, heartbeat, breathing, pain, balance, and internal tension. These signals influence mood, attention, and perception. A hill can look steeper when you are exhausted. A sound can feel more threatening when you are anxious. Time can seem slower during fear and faster during comfort or focus. The world you experience is not built from external signals alone. It is colored by the state of the body that receives them. Memory is another quiet architect of experience. You rarely meet the present as a blank observer. You meet it with a history. A smell can make a place feel familiar before you know why. A song can return a whole period of life in a sudden wave. A face can feel trustworthy, unfamiliar, comforting, or tense because of patterns learned over years. Memory does not simply store the past like a recording. It helps interpret the present. It tells the brain what matters, what to expect, what to ignore, and what may require action. This is also why two people can share the same physical environment but experience it differently. They may stand in the same street, under the same sky, hearing the same traffic, yet notice different things. One may see architecture, another may notice danger, another may feel nostalgia, another may think only about finding the way home. Their senses receive overlapping information, but attention, memory, emotion, and purpose shape the final experience. Reality is shared, but experience is personal. Attention acts like a spotlight, but it is more than a beam pointed at the world. It changes processing itself. When you attend to a sound, it becomes clearer. When you search for a friend in a crowd, faces become more important than signs, colors, or passing cars. When you are absorbed in thought, you may fail to notice something obvious in front of you. The brain has limited capacity, so it must choose. It cannot process every detail with equal depth. What feels like a complete world is partly the result of careful selection. The sense of time is also constructed. The brain does not contain a single simple clock that stamps every moment with perfect accuracy. Instead, time perception emerges from attention, memory, bodily rhythm, movement, and change. A minute filled with danger can feel long. An hour of deep focus can pass almost unnoticed. A boring wait can stretch, while a meaningful conversation can seem to vanish. Physical time may be measured by clocks, but lived time is shaped by the brain. Even the feeling of a continuous self is built through many processes working together. You feel like one person moving smoothly through life, but this unity depends on memory, body awareness, emotion, language, and social experience. The brain links the body you feel now with the memories of who you have been and the expectations of who you may become. It creates a practical center from which experience can be organized. This self is not fake, it is a real pattern, but it is maintained moment by moment. All of this matters deeply for the question of simulated reality. Before we ask whether the universe itself could be artificial, we have to notice that the world we experience is already a kind of internal model. It is not arbitrary because it is guided by real signals and tested by action. When you reach for a cup, your hand either finds it or does not. When you walk through a doorway, your body must fit through the opening. The brain's model succeeds because it remains connected to the physical world, but it is still a model. Your reality is not a direct download of the universe. It is a useful, embodied, constantly updated interpretation. This is not something to fear. In fact, it is what allows consciousness to exist in the form we know. Without interpretation, there would be no stable objects, no meaningful sounds, no familiar faces, no sense of place, and no flowing present. The brain does not trap you away from reality. It gives you a way to live within it. It turns waves, pressures, chemicals, motions, and internal signals into a world where you can move, learn, remember, and care. So as we continue toward the strange possibility that reality itself may have deeper layers, it helps to begin with the quieter truth close to home. The world you know is built gently and continuously inside awareness. It is shaped by the senses, held together by memory, softened or sharpened by emotion, and anchored by the body. For tonight, that can be a peaceful thought. Your brain has been building your world all day, carrying you through light, sound, movement, and meaning. Now it can begin to loosen its grip, let the details fade, and allow the world to become simple again. Breath, stillness, and the quiet feeling of being here. Chapter 3. From dreams to virtual worlds, why simulated experience feels possible. The idea of a simulated reality becomes much easier to understand when we notice that the human mind is already capable of entering worlds that are not physically present in the ordinary sense. Every night during sleep, the brain can create places, events, conversations, landscapes, and feelings without the outside world supplying them in the usual way. In a dream, you may find yourself walking through a city that does not exist, speaking with people who are not in the room, or returning to a place from childhood that appears with strange changes and impossible details. While the dream is happening, the experience can feel immediate. You do not usually stop and ask whether the street is real, whether the sky is consistent, or whether the person in front of you has a physical body. The dream presents itself as a world, and the dreaming mind often accepts it. Dreaming does not show that waking life is a simulation. That would be too large a leap. But it does show something important and scientifically grounded. The feeling of being inside a world does not require the full physical world to be present in the way it is during waking life. The brain can generate an immersive scene from memory, emotion, imagination, and internal activity. It can place a self inside that scene. It can give that self a point of view, a sense of movement, and a feeling that events are unfolding. Even when the dream is unstable, it can still feel lived from within. Sleep is not a simple shutdown of the brain. During dreaming sleep, many regions involved in imagery, emotion, memory, and sensation can become active, while some regions involved in careful self-monitoring and logical evaluation may be less engaged than during waking life. This helps explain why dreams can be vivid and emotionally powerful, yet strange inconsistencies may go unnoticed. You may accept a sudden change of location, an impossible building, or a person changing identity without surprise. The brain is producing experience, but the systems that normally test reality with strict attention are not working in the same way. This gives us an early clue about simulated experience. A convincing world is not only about detailed images. It is also about attention, expectation, memory, emotion, and the sense that what is happening matters. A dream can feel real even when it would fail a careful inspection, because the mind inside the dream is not inspecting it in the same way. The experience is carried by involvement. You are not looking at the dream from outside. You are participating in it. Imagination offers a gentler version of the same principle. When you read a story, you may picture a room, a landscape, or a face that has never been shown to you. The marks on a page or sounds in a voice do not contain a full visual world. Yet the brain borrows from memory, fills in missing details, and creates a mental space where events can happen. You know that this imagined world is not physically around you, but it can still affect your body. A tense scene can quicken your heartbeat. A peaceful description can soften your breathing. The boundary between physical input and inner experience is not simple. Human technology has learned to use this ability. A painting, a theater stage, a radio drama, a film, a video game, and a virtual reality headset all work by giving the brain selected signals and letting the brain complete the world. None of these needs to reproduce reality perfectly. A stage can become a forest with only lighting, sound, and gesture. A film can create fear, wonder, or sadness on a flat screen. A game can make a player care about a place made of rules, images, and choices. Virtual reality can add the powerful feeling that the environment surrounds the body. What makes virtual worlds especially interesting is the sense of presence. Presence is the feeling of being there, of occupying a space rather than merely observing an image. It depends on more than visual detail. It grows stronger when the world responds to movement. If you turn your head and the scene changes in a matching way, the brain treats the environment as more spatially stable. If you move your hand and see a virtual hand move with you, the body can begin to feel connected to the artificial space. If sound shifts with direction and distance, the world feels less like a display and more like a place. This does not mean the brain is easily fooled in every way. Virtual experiences can break down when timing is wrong, when movement does not match sensation, or when the body receives conflicting signals. Some people feel discomfort if the eyes report motion, while the balance system in the inner ear reports stillness. This mismatch reminds us that embodiment matters. The brain expects vision, balance, touch, and movement to agree. A simulated experience becomes more convincing when these channels support one another, and less convincing when they disagree. This is important for the larger question of simulated reality. A world does not need to imitate every detail equally. It needs to provide the right kinds of consistency for the beings inside it. In ordinary computer simulations, many details are simplified until they become relevant. A distant landscape may be less detailed than a nearby object. A game may calculate some events only when a player approaches them. These are practical shortcuts, not mysteries. But they help us imagine the broader idea. A constructed world might feel complete from within if it delivered stable patterns at the level its inhabitants could observe and interact with. Of course, our universe is not known to behave like a human-made game. The comparison is only a tool for thought. Nature is far richer and more deeply structured than any virtual world we can build. The physical universe displays consistency across enormous scales, from the behavior of particles to the motion of galaxies. Its laws are not just painted scenery. They can be measured, tested, and used to predict events with astonishing accuracy. If reality were simulated, it would have to be a simulation of extraordinary depth, far beyond the artificial environments we currently understand. Still, the progress of technology changes what feels imaginable. None of this proves that reality is simulated, but it shows that experience can be shaped by information in increasingly powerful ways. The deepest issue is not graphics or computing power. It is consciousness. A simulated world, in the meaningful sense, would not only show images, it would contain experience. There would have to be something it is like to be inside it. This is where the question becomes extremely difficult. We do not yet have a complete scientific explanation of how conscious experience arises from physical processes in the brain. We can study brain activity, perception, attention, memory, and behavior. We can connect changes in the nervous system with changes in experience. But explaining why subjective awareness exists at all remains one of the hardest problems in science and philosophy. Because of this, we must be cautious. A world can be simulated on a screen without anyone inside it being aware. Weather can be modeled without a storm feeling rain. A galaxy can be simulated without stars experiencing light. To imagine a simulated reality like ours, we must imagine not only a detailed environment, but also minds capable of having inner lives. Whether consciousness could arise inside a sufficiently complex artificial system is still an open question. Some thinkers believe it may be possible in principle. Others argue that biological embodiment may be essential in ways we do not yet understand. At present, no one can honestly claim the final answer. Dreams and virtual worlds help because they bring the question closer to ordinary experience. They show that the sense of being somewhere depends on patterns, perspective, memory, and response. They also show that experience is not all or nothing. There are degrees of presence. A daydream is faint. A film can absorb attention. A dream can feel total until waking. A virtual world can partly surround the senses. Waking life, by contrast, remains the most stable, coherent, and shared environment we know. That shared stability matters. In waking life, the world resists us. It does not change simply because we wish it to. Other people can examine the same object, return to the same place, and test the same event. Instruments can extend our senses and reveal patterns no unaided human could notice. This consistency is one reason science works. It does not remove the mystery of reality, but it gives us confidence that waking life is anchored in something independent of personal imagination. The simulation hypothesis enters precisely at this point. It asks whether that independent something might itself be built on a deeper layer of rules, information, or computation. It does not require us to deny the reality of experience. Instead, it invites us to ask what kind of foundation experience has. A dream is private and unstable. A virtual world is artificial and limited. Waking reality is shared, law-governed, and immensely detailed. But all three remind us that what feels like a world is always known from within a perspective. For a calm mind, this can be a beautiful thought rather than a disturbing one. We already live by trusting experience while knowing that it is shaped, filtered, and interpreted. We do not need to solve the deepest nature of reality before we can feel the warmth of a room, the quiet of the night, or the softness of breathing. The question can remain open, spacious, and gentle. And now, as this chapter fades, you can let the mind release the need to decide what is ultimate. Dreams, virtual worlds, and waking life all pass through awareness like different kinds of light. For tonight, it is enough to rest inside the world that is here, steady enough to hold you, soft enough to let you sleep. Chapter 4. The Simulation Hypothesis, a modern version of an ancient doubt. The simulation hypothesis feels modern because it uses the language of computers, but the doubt beneath it is much older than technology itself. how can a mind inside reality know what reality truly is? For as long as human beings have thought carefully about existence, there has been a quiet unease about appearances. The world seems solid, bright, and immediate. We open our eyes, move through rooms, recognize faces, feel the weight of objects, and assume that we are meeting reality as it is. Yet reflection introduces a distance between experience and certainty. We can be mistaken. We can misread what we see. We can believe something strongly and later discover that the world was different from how it appeared. From that simple fact grows a deeper question. If small errors are possible, could there also be a much larger error hidden underneath ordinary life? Ancient philosophy often returned to this problem. Some thinkers imagined human beings mistaking shadows for truth, living inside a limited picture of the world, while a deeper order remained unseen. Others asked whether waking life could ever be fully distinguished from a dream from the inside. These were not scientific claims in the modern sense. They were tools for thinking about knowledge. Their purpose was not to prove that ordinary reality is false, but to reveal that confidence is not the same thing as certainty. A person can feel completely surrounded by a world and still ask whether there is a deeper layer behind it. The simulation hypothesis belongs to this same family of questions. It does not begin with a telescope, a particle accelerator, or a measured signal from beyond the universe. It begins as a thought experiment. It asks whether a sufficiently advanced civilization, using technology far beyond our own, could create a detailed artificial world containing conscious beings who experience that world from the inside. If that were possible, then those beings might study their universe, discover patterns, build sciences, argue about meaning, and never directly perceive the deeper reality in which their world was running. This is why the idea is so strange. It does not simply say that reality might be artificial, the way a painted landscape is artificial. It suggests that an entire experienced world might be produced by a deeper system of rules. From inside, such a world might not look crude or fake. It might have stars, atoms, weather, bodies, memory, history, and uncertainty. Its inhabitants might have no obvious access to whatever supports their existence. The question is not whether our current computers can do this. They cannot. The question is whether any physical system, in principle, could generate conscious experience inside a structured environment. The modern form of the idea became more plausible to imagine because we now understand something about simulation itself. We build simplified models of weather, galaxies, traffic, cells, economies, and ecosystems. These models are not the things they represent. A simulated storm does not wet the ground. A simulated galaxy does not shine in the sky. But simulations can capture patterns, relationships, and consequences. They allow one system to imitate the behavior of another according to rules. As computing improves, the gap between model and appearance can narrow in certain limited domains. This does not prove anything about the universe, but it gives the old philosophical doubt a new technical vocabulary. There is also a second ingredient, the possibility of future intelligence. If civilizations can survive long enough, and if technology continues to advance, they may develop forms of computation that we can barely imagine. They might not resemble our machines. They might use physical principles we do not yet know how to use. They might build simulations for science, history, education, entertainment, ethics, or reasons that would be incomprehensible to us. The simulation hypothesis often rests on this chain of possibility. If conscious simulated worlds could be built, and if many such worlds were built, then one might ask whether experienced beings are more likely to find themselves in a fundamental world or in one of many simulated worlds. This reasoning is provocative, but it is not proof. It depends on several large assumptions. We do not know whether consciousness can arise in an artificial system. We do not know whether advanced civilizations commonly survive long enough to create such systems. We do not know whether they would want to. We do not know whether the resources required would be physically possible. We do not even know whether the idea of simulating a whole universe containing conscious beings is coherent in the way it is often imagined. Each step may sound possible, but possibility is not the same as evidence. This distinction matters because the simulation hypothesis can easily become more dramatic than careful. It is tempting to treat every mystery as a clue. The strange behavior of quantum systems, the mathematical nature of physical law, the limits of observation, or the fact that the universe has stable rules may all feel suggestive. But feeling suggestive is not enough. A genuine scientific claim must do more than fit a mood. It must help us explain observations in a way that can be checked. It must risk being wrong. If an idea can absorb every possible result, then it may be interesting, but it becomes difficult to test. For example, if someone says that any observation we make is simply part of the simulation, then no observation could count against the idea. If the universe appears continuous, the simulation is well made. If the universe appears grainy at some deep level, that is also taken as evidence. If physics is elegant, it is code. If physics is messy, it is still code. This kind of reasoning is too flexible. It protects the idea from failure, but it also weakens it as science. A theory that explains everything in advance may end up explaining very little. A more careful approach is to ask whether the hypothesis could lead to specific expectations. Would a simulated universe show limits of resolution? Would there be detectable shortcuts? Would the laws of physics reveal computational constraints? Would extremely high energy processes expose a hidden grid or boundary? These are fascinating questions, but they remain speculative. Our current understanding of physics already includes limits, uncertainty, and deep structure without requiring a simulation. A smallest meaningful scale, if it exists, would not automatically mean pixels. Mathematical regularity would not automatically mean programming. Hidden order would not automatically mean design. This is where the ancient doubt and modern science meet. Philosophy teaches humility about certainty. Science teaches discipline about evidence. Together they let us explore strange possibilities without surrendering to them. We can admit that our experience may not reveal the deepest layer of existence. At the same time, we can also admit that not every imaginable deeper layer is equally supported. The simulation hypothesis is valuable when it sharpens our questions about reality, information, consciousness, and knowledge. It becomes less valuable when it pretends to be settled fact. There is another problem that makes the idea even more difficult. If our world were simulated, then the world containing the simulators would still need explanation. What is that higher reality made of? Does it have laws? Did it begin? Why does it exist? Could it also be simulated? The hypothesis may move the mystery upward rather than remove it. Instead of asking why our universe exists, we ask why the larger system exists. Instead of asking why physical laws work here, we ask why deeper laws work there. The ultimate question remains: Yet this does not make the idea meaningless. Many scientific and philosophical ideas are useful not because they end all questions, but because they rearrange them. The simulation hypothesis encourages us to ask what reality would look like from the inside if its foundation were hidden. It asks what kinds of evidence matter. It asks whether consciousness depends on the material that produces it, or on the organization of processes. It asks whether a world can be real for its inhabitants, even if it is not the lowest level of existence. These are serious questions, even if the answers remain unknown. It is also important to notice that the hypothesis does not necessarily make life trivial. Some people hear the word simulation and imagine that everything would become meaningless, as though a simulated foundation would turn love, pain, beauty, memory, and responsibility into illusions. But this does not follow. The meaning of an experience depends partly on the beings who have it and the relations it creates. A friendship inside a simulated world, if conscious beings truly experienced it, would still be a real relationship within that world. A discovery would still be a discovery. A choice would still shape a life. The layer beneath reality might change our metaphysics, but it would not automatically erase value. In a scientific spirit, the honest position is neither belief nor dismissal. We do not know that reality is a simulation. We also do not know enough about consciousness, computation, and ultimate physical law to declare every version impossible. The reasonable path is to treat the idea as a strange mirror. It reflects back our uncertainty about perception, our growing power to create artificial environments, our limited understanding of mind, and our deep desire to know whether the world is final or only one layer of something larger. So the simulation hypothesis is not merely a story about future machines. It is a modern doorway into an ancient human problem. We stand inside experience, using the tools of experience to ask what experience is made of. We build theories from within the world, never from outside all worlds. We search for foundations while standing on a foundation we do not fully understand. And for now, that is enough. The question can remain open without becoming heavy. You do not have to solve the nature of reality tonight. You can simply notice the quiet wonder of being here at all, inside a world that holds together gently enough for thought, breath, and rest. Chapter 5: Reality as Information, the Universe Beneath Matter. If reality could ever be compared to a simulation, the comparison begins not with glowing screens or artificial worlds, but with a quieter and more scientific idea. The universe may be understood, at its deepest levels, as patterns of information. In ordinary life, matter feels like the most basic thing there is. A stone feels hard, water feels fluid, air feels invisible but present. Your body feels warm, solid, and located in space. It is natural to imagine reality as a collection of objects, each made from smaller objects, until we eventually reach the tiniest building blocks. This picture is useful. It helps us navigate the world. It helps us understand chemistry, biology, and machines. But modern physics has gradually shown that matter is not quite as simple as small solid pieces arranged in space. Beneath the familiar surface of things, nature looks more like structure, relation, energy, and information. Information in this scientific sense does not mean a message written by someone. It does not have to involve a mind, a sentence, or an intention. Information means that a physical system can be in different possible states, and that those states can make a difference. A coin lying on a table can be heads or tails. A switch can be on or off. A particle can have different measurable properties. A field can have different configurations. Whenever the state of something matters, whenever there is a distinction that can be preserved, changed, measured, or transferred, information is present in a physical sense. This may sound abstract, but it is deeply practical. A book contains information because the ink marks differ from place to place in meaningful patterns. A computer stores information because its physical components can be arranged in different stable states. A living cell carries information in chemical structures that influence how it grows, repairs itself, and interacts with its environment. Even a footprint in dust contains information, because its shape tells us something about what passed through. Information is not separate from matter. It is carried by matter, energy, and physical structure. The surprising part is that physics increasingly treats information not as an afterthought, but as something woven into the behavior of the universe. When we describe a physical system, we are often asking what information is needed to specify its state. Where is it? How fast is it moving? What energy does it have? What arrangement is it in? What can be known about it and what cannot? These questions are not only about human knowledge, they reflect real limits and relationships in nature. The possible states of a system shape what it can do. Consider heat. At the everyday level, heat feels like warmth flowing from one thing to another. But beneath that sensation is the motion and arrangement of many microscopic parts. A hot object has energy distributed among countless tiny movements. A cold object has less of that kind of disorderly motion. Temperature is not a property of a single simple object in isolation, in the same way color appears to be. It emerges from the collective behavior of many parts. To understand heat, we must think about the number of possible microscopic arrangements that could produce the same large-scale condition. That is already an informational way of thinking. This connects to entropy, one of the deepest concepts in physics. Entropy is often described as disorder, but that word can be misleading. More carefully, entropy is related to how many microscopic arrangements correspond to the same visible state. A neatly stacked deck of cards has fewer possible arrangements than a shuffled deck. A gas spread evenly through a room has many more possible microscopic configurations than a gas compressed into one corner. Nature tends to move toward states that can happen in more ways. This is why many processes have a direction. Ice melts in warm water, smoke spreads in air, and broken eggs do not spontaneously rebuild themselves. Beneath these changes is a story about information, probability, and the number of possible arrangements hidden under what we see. Matter itself also becomes stranger when examined deeply. The objects around you are made of atoms, but atoms are not miniature versions of familiar objects. They are structured systems governed by quantum rules. Electrons do not orbit the nucleus like tiny planets. They are described by quantum states, which tell us about possible measurement outcomes. At the deepest levels currently described by physics, particles are understood as excitations of fields. A field is not a solid substance in the ordinary sense. It is something spread through space, capable of carrying energy and producing particles when excited in particular ways. What we call matter is therefore not simply little lumps of stuff. It is organized activity in underlying fields. This does not make matter unreal. It makes matter more subtle. A chair is real because it has stable structure, resists your body, reflects light, and participates in cause and effect. But the chair is not fundamental in the way it feels to the hand. Its solidity comes from electromagnetic interactions and quantum behavior among its atoms. Its shape is maintained by bonds and forces. Its color depends on how it interacts with light. The familiar object is an emergent pattern, a large-scale result of deeper processes. Reality appears solid because the underlying patterns are stable enough for bodies like ours to live among them. Information becomes especially important in quantum physics. A quantum state contains everything the theory can say about a system before measurement. It does not always give a definite answer in advance for every possible question. Instead, it gives probabilities. This does not mean that the universe is simply vague because we are ignorant in an ordinary way. Quantum theory suggests that nature itself does not always assign familiar definite properties before interaction. When systems interact, information is exchanged, correlations are formed, and outcomes become part of the larger physical story. One of the most striking features of quantum physics is entanglement. When systems become entangled, their states cannot be fully described separately, even if the systems are later far apart. The whole contains information that is not reducible to each part alone. This is not a signal traveling faster than light, and it does not allow ordinary messages to be sent instantly across space. But it does show that the structure of information in the quantum world is unlike the structure of information in everyday objects. The universe is not merely a pile of independent pieces. It contains deep relationships. Black holes make the informational view even more powerful. A black hole is an object whose gravity is so strong that beyond a certain boundary, not even light can escape. For a long time, black holes seemed like places where information might disappear forever. If matter fell in, perhaps all the details of what formed the black hole would be lost, leaving only a few large-scale properties visible from outside. But this idea creates a profound tension with quantum physics, where the evolution of information is expected to follow strict rules. The question of whether information is lost in black holes remains one of the deepest puzzles in theoretical physics. The mystery became even richer when physicists discovered that the entropy of a black hole is connected not to its volume, but to the area of its boundary. That is a strange and beautiful result. For ordinary objects, we might expect the information capacity to depend on how much space is inside. But black holes suggest that, in gravitational systems, the amount of information associated with a region may be connected to the surface surrounding it. This idea helped inspire broader thinking about whether the information content of space might be encoded in unexpected ways. It does not prove that the universe is a simulation, but it does suggest that reality may be more boundary-like, relational and informational than ordinary intuition expects. This is where the simulation question begins to return. A simulated world, in the broad sense, is made from information and rules. Its visible objects are not fundamental in themselves. They arise from deeper states and processes. Our universe, too, can be described through states, rules, fields, probabilities, and relationships. But we must be very careful. Describing reality with information does not automatically mean reality is computed by something outside itself. A river can be described mathematically without being made by a mathematician. A snowflake can contain complex structure without being designed. Natural law can generate patterns without intention. The universe may be informational in the sense that physical states and their possible transformations are central to its behavior. That is different from saying the universe is artificial. The scientific point is subtler and more interesting. Matter may not be the final language of reality. Objects may be stable appearances of deeper structures. Space, time, energy, and information may be connected in ways we do not yet fully understand. If there is a deeper layer beneath the universe we observe, it may not resemble matter as we imagine it. It may be a structure of relations from which matter emerges. This shift in thinking changes how we understand ourselves as well. The human body is matter, but it is also information in motion. Your cells maintain patterns. Your nervous system carries signals. Memory depends on physical changes that preserve traces of experience. Perception depends on the flow and transformation of information. A living being is not just a collection of atoms. It is an organized process that holds itself together for a time. The same atoms arranged randomly would not be you. What matters is the pattern, the structure, the ongoing activity. This does not make life less real or more mechanical. If anything, it makes existence more delicate and remarkable. You are a temporary pattern in the universe, but not a meaningless one. Patterns can think, feel, remember, and wonder. They can ask what matter is, what information is, and whether reality has a deeper foundation. The universe has produced arrangements complex enough to question the nature of arrangement itself. So when we say reality may be understood through information, we are not reducing the world to something cold or empty. We are noticing that beneath the hardness of matter and the flow of time, there may be a deeper language of states, distinctions, relationships, and transformations. This language does not answer the simulation question by itself, but it makes the question more serious because it shows that the world we touch is not the final level of explanation. Beneath matter, there is structure. Beneath structure, there may be information. Beneath information, there may be laws we have only begun to glimpse. And for tonight, that thought can be allowed to settle softly. The world around you does not need to become less real, because it is deeper than it appears. It can simply become quieter, more spacious, and more mysterious. Beneath every object, every sound, and every breath, reality is holding its patterns together, gently enough for you to rest inside them. Chapter 6. The pixel question: could space and time be discrete? One of the strangest possibilities in modern physics is that space and time, which feel perfectly smooth to us, may have a hidden structure so small that ordinary experience can never notice it. When you look across a room, space seems continuous. There appears to be no smallest step between here and there. You can imagine dividing the distance in half, then in half again, and then again without end. Time feels similar. A second can be divided into smaller moments, then smaller still, until the mind begins to lose its grip. In everyday life, this smoothness is so natural that we almost never question it. A hand moves through the air, a shadow crosses a wall, a sound fades into silence, and everything seems to pass through an unbroken flow. But physics often teaches us that what feels smooth at one scale can be made of structure at another. Water in a glass looks continuous, yet it is made of molecules. A metal surface can look perfectly flat, yet under magnification it has texture, gaps, and atomic order. Light can behave like a wave, spread out and flowing, yet it can also be exchanged in indivisible packets of energy. The lesson is not that everything must be made of tiny pieces in a simple way. The lesson is that human senses are not designed to see the deepest scale of nature. What feels continuous may sometimes be the large-scale appearance of something more subtle underneath. This is the heart of the pixel question. Could space itself have a smallest meaningful unit? Could time have a smallest meaningful interval? Is reality like an image that appears smooth from far away, even though it is built from smaller elements? The word pixel is only a metaphor. It comes from digital images, where a picture is made of tiny units that are not visible unless you zoom in enough. The universe is not known to be a screen, and space is not known to be made of little square blocks. But the metaphor helps us ask whether continuous space and continuous time are truly fundamental, or whether they are smooth appearances of a deeper physical structure. The most famous scale connected with this question is the Planck scale. It is formed by combining basic constants of nature associated with gravity, quantum theory, and the speed of light. The Planck length is incredibly small, far beyond anything we can directly measure with current instruments. The Planck time is the time light would take to cross that tiny distance. These scales do not automatically mean that space and time are made of pixels. This is a common misunderstanding. The Planck length is not confirmed as the size of a smallest piece of space. Instead, it marks a realm where our current theories are expected to stop working in their usual form, and where a theory of quantum gravity may be needed. This matters because our two greatest descriptions of nature do not fit together smoothly at the deepest level. General relativity describes gravity as the curvature of space-time. In this view, space and time are not a fixed background. They are dynamic, able to stretch, bend, and respond to matter and energy. Quantum theory, on the other hand, describes the behavior of matter and energy at small scales, where uncertainty, probability, and quantized interactions become essential. Each theory is extremely successful in its own domain. But when we try to describe places where gravity is very strong and quantum effects should also matter, such as the earliest universe or the interior of black holes, the combination becomes difficult. The pixel question appears in this gap. If space-time can bend like a smooth fabric in general relativity, but nature also behaves quantum mechanically at small scales, then perhaps space-time itself has quantum properties. It might not be smooth all the way down. It might fluctuate, become uncertain, or be built from more basic relations. Some approaches to quantum gravity suggest that areas or volumes may come in discrete amounts. Others suggest that space-time might emerge from networks of relationships rather than exist as a pre-existing container. Still others keep space-time continuous, but change our understanding of fields and gravity within it. No single answer has been confirmed. It is important to separate discreteness from graininess in the ordinary sense. If space were discrete, that would not necessarily mean tiny cubes floating in emptiness. There may be no deeper empty stage in which such cubes sit. Space is what gives meaning to distance and location. If space is not fundamental, then asking what its pieces are inside may be the wrong question. A deeper theory might describe relationships first, with distance emerging later. In that case, the familiar space around us would be like a large-scale pattern, not a pile of miniature bricks. Time brings its own difficulty. We experience time as a sequence, with events ordered as before and after. Clocks measure intervals with remarkable precision. In relativity, time is woven together with space into space-time, and different observers can measure time differently depending on motion and gravity. If time were discrete, it would not simply mean that the universe clicks forward like a mechanical clock, in the way a film advances frame by frame. That image is tempting, but too simple. A deeper theory would have to preserve the successful predictions of relativity and quantum physics. It would have to explain why time appears smooth, why physical laws work so precisely, and why no obvious universal ticking has been observed. This is one reason the simulation comparison must be handled carefully. In a computer image, pixels are evidence of a digital representation. If reality had a smallest scale, some people might be tempted to call it evidence of computation. But discreteness in physics would not prove that the universe is artificial. Many natural systems have discrete properties without being simulations. Atoms have quantized energy levels. Electric charge comes in units. Angular momentum can be quantized. These facts tell us that nature has structure, not that someone programmed it. If space-time has discrete features, that would be a profound discovery, but it would not automatically answer why reality exists or whether it was created by an outside system. There are also reasons physicists are cautious. If space had a simple grid, like the grid in a digital image, it might affect how particles move at extremely high energies. It could create slight differences depending on direction, because a grid has preferred axes. Yet the known laws of physics appear to respect deep symmetries with extraordinary precision. The speed of light in empty space, the behavior of particles, and the structure of relativity all place tight constraints on simple forms of discreteness. This does not rule out every possible deeper structure. It simply means that if space-time is discrete, it must be discrete in a way that does not obviously break the symmetries we observe. Another challenge is measurement. To probe smaller distances, we generally need higher energies. But at some point, concentrating too much energy into a tiny region may create gravitational effects strong enough to prevent further probing. This suggests that nature may have an operational limit to how finely distance can be measured. Yet an operational limit is not necessarily the same thing as a literal smallest piece. It may mean that our concepts of distance and time stop being useful beyond a certain scale. The early universe makes this question especially important. When cosmologists trace the expansion of the universe backward, they reach conditions of extreme density and temperature. Our current theories can describe much of the early cosmic story with great success, but not the absolute beginning in a complete way. Near that boundary, quantum gravity may be essential. If space-time itself changes character at such scales, then the beginning of the universe may not be a simple point where everything was squeezed into ordinary space. It may involve a phase where space and time, as we understand them, were not yet fully formed. Black holes point toward the same mystery. At the center of a black hole, classical general relativity predicts a singularity, a place where the mathematics indicates that curvature becomes extreme and the theory can no longer give a complete physical description. Most physicists do not treat this as proof that an actual infinite physical point exists. Instead, it is often understood as a sign that the theory is being pushed beyond its range. A deeper theory may replace the singularity with something else, perhaps involving quantum spacetime. There's a quiet humility in all of this. The pixel question is easy to state, but hard to answer. It asks whether the smooth stage of life, the space where we move and the time through which we age, is truly basic or only an emergent appearance. It asks whether continuity is fundamental or approximate. It asks whether there is a lowest level of resolution, or whether the very idea of resolution belongs only to the world above a deeper theory. For now, the honest answer is that we do not know. Space and time may be continuous. They may be discrete. They may be neither in the simple sense we imagine. The deepest layer may require concepts that do not fit ordinary language at all. What we can say is that physics has already taught us to distrust the obviousness of everyday experience. Solid things are not solid in the naive sense. Empty space is not simple nothingness. Time is not universal in the way it feels. So it is not unreasonable to wonder whether space and time also hide a structure beneath their smooth surface. And yet, this mystery does not disturb the world around you. The room remains quiet. The night still unfolds gently. Whether space-time is smooth, discrete, or something stranger than either, it holds your breathing, your rest, and this small moment of awareness. You do not need to see the deepest scale of reality tonight. It is enough to let the surface become soft, continuous, and calm. Chapter 7. The Quantum Clues: Observation, Probability, and Unfinished Reality. Quantum physics gives the simulation question its most delicate kind of mystery, not because it proves that reality is artificial, but because it shows that the world is far less finished, solid, and obvious than it appears. In ordinary life, objects seem to possess their properties whether anyone checks them or not. A cup is on the table before you look. A door is either open or closed. A stone has a position, a shape, and a weight. The everyday world feels definite. It seems to be made of things that already are what they are, waiting for us to notice them. This expectation is so natural that we rarely think of it as an assumption. But at the quantum level, where physics studies atoms, particles, and the smallest interactions of matter and energy, this familiar picture no longer works in the same simple way. Quantum physics does not say that anything can happen for no reason. It is not chaos. In fact, it is one of the most precise and reliable frameworks ever created in science. It allows physicists to understand atoms, chemistry, lasers, transistors, magnetic resonance imaging, and modern technology. Yet the picture it gives us of reality is deeply strange. It tells us that before certain measurements are made, a system may not have a single definite value for every property we might ask about. Instead, it is described by a quantum state, a mathematical description that gives probabilities for possible outcomes. Here's the important point. Probability is not merely a sign that we are ignorant. If you hide a coin under your hand, it is already heads or tails, even if I do not know which. Quantum uncertainty is different. In many situations, the best available theory does not describe a hidden definite answer, waiting quietly underneath. It describes a range of possible outcomes, with probabilities attached to them, until an interaction produces a definite result. This does not mean the universe is vague in every way. Quantum systems follow strict rules. The probabilities are not random guesses. They evolve in an orderly mathematical way, and experiments confirm those predictions with extraordinary accuracy. The mystery is that the order is not the same kind of order we see in ordinary objects. It is an order of possibilities, tendencies, and relationships, rather than a simple inventory of pre-existing facts. The famous experiment with particles passing through narrow openings captures this strangeness beautifully. When small particles such as electrons are sent through an arrangement where they can travel by more than one path, they can produce a pattern that looks like the behavior of waves. It is as if the possible paths interfere with each other. But when the experiment is arranged so that the path is measured, the wave-like pattern disappears, and the outcomes become more particle-like. The act of measurement changes what can be observed. This phrase, act of measurement, is often misunderstood. It does not mean that a human mind must look at something to make it real. In physics, observation means physical interaction. A detector, a screen, a photon, an atom, or the surrounding environment can all count as part of the measured process if they interact with the system in a way that produces a stable record. Consciousness may notice the record later, but it is not required for the basic physical event. This point is essential. Quantum physics is mysterious enough without adding claims that it does not support. So what is measurement? At the simplest level, it is the moment when a delicate quantum system becomes linked with something larger and more stable. A tiny system that could be described in terms of multiple possible outcomes interacts with a measuring device or with the environment, and the result becomes recorded in the larger world. The record may be a mark on a detector, a changed energy level, a flash of light, or some other physical trace. Once that trace spreads into the environment, the different possibilities no longer remain available to us in the same coherent way. This process is connected with decoherence, a key idea in modern physics. Decoherence happens when a quantum system becomes entangled with its surroundings in such a complex way that its wave-like alternatives stop behaving as if they can interfere with one another. The environment carries away information about the system. From our perspective, the world begins to look classical, definite, and familiar. Decoherence helps explain why we do not see cats, tables, or planets behaving like delicate quantum superpositions. Large objects are constantly interacting with air, light, heat, and countless other degrees of freedom. Their quantum possibilities become dispersed into the environment almost instantly. But decoherence does not, by itself, settle every philosophical question. It explains how quantum behavior becomes effectively hidden and why ordinary reality appears stable. It does not fully answer why one particular outcome is experienced rather than another, at least not in a way that everyone agrees on. This is known as part of the measurement problem. It is one of the reasons quantum physics still inspires debate. The equations work beautifully, but what they mean about reality remains open to interpretation. Different interpretations of quantum physics try to answer this in different ways. Some treat the quantum state mainly as a tool for predicting what we will observe. Some suggest that all possible outcomes occur, but in separate branches of reality. Some propose that hidden variables guide quantum behavior beneath what we can see. Others suggest that the quantum state sometimes physically collapses into a single outcome. Each approach tries to preserve the success of the mathematics while explaining what is actually happening. None has become universally accepted as the final word. This is where the phrase unfinished reality becomes useful, but only if we use it carefully. It does not mean that the world is imaginary until we look. It means that, at the quantum level, reality does not always resemble a fully detailed classical picture existing independently of all interaction. Some properties seem to become definite through the way systems interact, measure, and become correlated with their environments. Reality is not unfinished in the sense of being unreal. It is unfinished in the sense that the old everyday categories of object, property, and observation are not deep enough. The connection to the simulation question is easy to feel. In some artificial worlds, details may become fully specified only when they are needed, when a player enters a region or when a system must calculate a result. It is tempting to compare this with quantum measurement and say that the universe renders itself when observed. But this comparison can mislead. Quantum physics was not invented as a theory of computational shortcuts. It is a theory of physical systems, tested through experiments, and its strangeness follows strict mathematical rules. Measurement matters, but that does not prove an outside machine. Still, the comparison remains interesting as a metaphor. Quantum physics teaches us that the world is not simply a fixed picture with every detail already painted in the way common sense expects. It is more like a rule-governed structure in which possibilities, interactions, and records matter deeply. The universe appears to generate definite events through physical processes, not through passive existence alone. That does not make it artificial, but it does make it less like the solid stage we imagine and more like a dynamic network of relationships. Another clue comes from the limits of knowledge built into quantum theory. Some pairs of properties cannot both be known with unlimited precision at the same time. This is not because our instruments are clumsy. It is part of how quantum states work. The more precisely one property is defined, the less precisely the complementary property can be defined. This points to a structural feature of nature. The universe does not always allow the kind of complete description that classical physics once promised. This is a profound shift. Classical physics suggested that if a mind could know the exact state of everything, it could, in principle, predict the future perfectly. Quantum physics changed that dream. It did not destroy causality in a simple way, and it did not make science impossible. Instead, it replaced certainty with lawful probability. The future is constrained, shaped, and patterned, but not always predetermined in the old mechanical sense. At the smallest scales, nature seems to preserve a kind of openness. For the simulation hypothesis, this openness is not evidence, but it is relevant. If reality were simulated, one might expect it to operate through rules that generate outcomes rather than store every classical detail in advance. Quantum physics already tells us that our universe is not built from classical details in advance, at least not in any simple confirmed way. But the scientific conclusion is modest. Quantum mechanics reveals a deep and strange architecture of probability. It does not reveal programmers. It does not reveal a screen. It does not reveal a world outside our own. What it does reveal is emergence. The stable world of chairs, planets, bodies, and clocks arises from a deeper layer where possibility, interaction, and information behave in unfamiliar ways. The classical world is not false. It is the large-scale face of a quantum universe. It is what appears when countless interactions become stable enough for memory, measurement, and life. That may be the calmest way to hold the mystery. Quantum physics does not tear the world away from us. It does not say that your room is unreal or that your thoughts are meaningless. It says that the foundations beneath them are richer than common sense can picture. The world is steady enough to live in, but strange enough to wonder about forever. So tonight, the quantum clues can remain what they are. Clues, not conclusions. Observation matters, but not because the mind magically creates the moon. Probability matters, but not because the universe is careless. Unfinished reality matters, but not because reality is empty. Beneath the familiar surface, nature is still working quietly, turning possibility into experience, interaction into memory, and mystery into the gentle shape of the present moment. Chapter 8. Could we ever detect the code? If reality were somehow built on a deeper layer of rules, one of the most fascinating questions would be whether beings inside that reality could ever notice the hidden structure beneath their world. The word code is useful, but it must be treated carefully. In everyday language, code suggests instructions written by a programmer, like the hidden machinery behind a digital environment. In physics, however, the deeper rules of nature are not known to be written by anyone. They are mathematical patterns that describe how matter, energy, space, time, and fields behave. So when we ask whether we could detect the code, we are not necessarily looking for letters, messages, or deliberate signatures. We are asking whether the universe might contain physical traces of a deeper system that generates the reality we observe. This is a difficult question because any inhabitants of a world can only test that world from within. We cannot step outside the universe, look back at it from a higher level, and inspect its foundation from the outside. Every experiment we perform uses the materials, forces, clocks, measuring devices, and laws available inside the universe itself. If there is a deeper layer, we do not have direct access to it. We can only look for places where our current understanding becomes incomplete, strained, or unexpectedly patterned. Science has faced similar challenges before. No one can see an atom with ordinary vision, yet the existence of atoms became clear through many indirect effects. No one can watch space-time curve with the senses alone, yet gravity reveals its geometry through motion, light, and time. No one can see the deep interior of a star directly, yet physics can infer what happens there from light, particles, and models. Science often detects the hidden by studying its consequences. If a deeper layer of reality affects what we can measure, then in principle it might leave evidence. But the simulation hypothesis is harder than many hidden things in science because it may be too flexible. A physical theory usually becomes testable when it makes a specific prediction. It says that if the world works this way, then under certain conditions we should observe one result rather than another. A vague simulation idea may not do that. If every possible observation can be explained by saying the simulation chose to appear that way, then the idea becomes impossible to test. It may remain interesting as philosophy, but it becomes weak as science. A more scientific version would need to suggest a detectable difference between a simulated universe and a non-simulated one. For example, if reality were generated by a finite process, perhaps there would be limits to resolution. Perhaps space would not remain smooth at all scales. Perhaps extremely energetic particles would reveal tiny irregularities in the structure of space-time. Perhaps there would be a highest possible information density, a deepest level beyond which ordinary concepts of distance and time stop working. These are not proofs of simulation. They are possible areas where deeper physics might leave clues. One imagined clue is a hidden grid. Human-made simulations often use grids, meshes, or discrete steps to calculate physical behavior. If the universe were based on a simple grid, then at very high energies, particles might behave slightly differently depending on direction, because the grid would quietly choose preferred directions in space. That would conflict with the observed symmetry of nature, where the laws of physics appear to work the same regardless of direction or uniform motion. Experiments and astronomical observations already place very strong limits on such simple grid-like ideas. If there is a deeper structure, it must be subtle enough to preserve the symmetries that our instruments see. Another possible clue would be a limit in how much information can be stored in a region of space. Physics already suggests that information, energy, gravity, and boundaries are connected in surprising ways. Black holes are central to this discussion because their entropy is tied to the area of their boundary, not simply the volume inside. This does not mean black holes are computer files or that the universe is digital in the ordinary sense, but it does show that the universe treats information as a physical quantity with limits. If reality has a maximum information capacity, that fact could be part of a deeper natural law. It could also be the kind of feature someone might loosely compare to a computational limit. The comparison is interesting, but it is not evidence by itself. Some people wonder whether randomness could reveal the code. Quantum physics includes events that appear probabilistic, and the outcomes cannot be predicted exactly in individual cases. One might imagine that if reality were computed, its randomness might eventually show patterns, like a poor random number generator. But quantum randomness has been tested with great care, and so far it behaves in ways consistent with quantum theory. Even if hidden patterns were found, they would not automatically imply simulation. They might point to a new physical theory, hidden variables, or some deeper law of nature. Once again, a strange result would open questions before it answered them. The cosmic background light from the early universe is another tempting place to look for clues. It carries a faint record of conditions from a very young cosmos. Its tiny variations helped seed the large-scale structure of galaxies and clusters. If the universe had unusual large-scale patterns, boundaries, or repeated structures, perhaps traces might appear in this ancient light. Scientists already study it for signs of inflation, curvature, topology, and new physics. But using it to prove simulation would be extremely difficult. Natural cosmology offers many possible explanations for patterns, and randomness can produce surprising shapes without design. We might also ask whether physical laws look too mathematical. The universe can be described with remarkable precision, and this elegance can feel almost suspicious. Yet mathematics is the language we use to describe regularity. If nature contains stable relationships, mathematics will naturally be powerful. The success of mathematics does not necessarily mean reality is made of code in the human sense. It may mean that the universe has structure, and minds evolved inside it have learned to express that structure abstractly. A map can be beautifully mathematical without implying that the landscape was designed as a map. Another possible route would be to search for errors, glitches, or inconsistencies. In fiction, simulated worlds reveal themselves through repeated patterns, impossible events, or moments where the rules fail. Real science is much stricter. An unexplained event is not automatically a glitch. Instruments fail. Data can be noisy. Human interpretation can be wrong. Rare natural events happen. Before claiming a crack in reality, scientists must rule out ordinary error, unknown but natural processes, and limitations in measurement. The history of science is full of anomalies that became new physics, and also anomalies that disappeared when experiments improved. This caution is essential because the human mind is very good at finding patterns. We notice coincidences. We remember strange moments. We connect events that may have no deeper relation. In daily life, this tendency can be useful because recognizing patterns helps us learn and survive. In science, however, it must be balanced by careful testing. A real clue must be repeatable, measurable, and connected to a clear prediction. A feeling that reality seems strange is not enough. Reality has always seemed strange when seen more deeply. There's also a possibility that no detectable code exists, even if the simulation idea were true. A sufficiently advanced simulation might be built so that its inhabitants could never observe the underlying layer. Its rules might be perfectly self-consistent from the inside. Every experiment might simply reveal more of the simulated physics. In that case, the hypothesis would not be scientifically accessible. It would become like asking whether the entire universe was created a moment ago with all memories already in place. If no observation could ever distinguish that idea from ordinary reality, then science has no path to test it. This is not a failure of science. It is part of what makes science powerful. Science does not answer every question that can be spoken. It answers questions that can be connected to observation, measurement, and evidence. The simulation hypothesis becomes scientific only where it makes contact with possible evidence. Without that contact, it may still inspire thought about consciousness, information, and existence, but it should not be treated as established knowledge. So, could we ever detect the code? The honest answer is maybe, but only if the deeper layer leaves physical traces that differ from what our best natural theories predict. We might find unexpected limits in spacetime, unusual information bounds, broken symmetries, unexplained correlations, or new behavior at extreme energies. But any such discovery would first be new physics. Calling it code would require much more. We would need evidence not only that reality has deeper structure, but that this structure is best understood as generated, artificial, or computational in a specific sense. For now, the search itself may be more valuable than the answer. By asking how reality could be tested from within, we learn what science can and cannot do. We learn the difference between mystery and evidence. We learn that a question can be profound without being settled. And we learn that the universe, whether fundamental or layered, continues to invite careful attention. Tonight, that uncertainty can remain open and calm. There is no need to find hidden code in the walls of the world. The laws we know are holding steady. The stars are not flickering with secret messages. Reality, whatever its foundation, is quiet enough to rest inside, and deep enough to keep wondering about when morning comes. Chapter 9. The problem with the simulation idea. The simulation idea is fascinating because it seems to open a hidden door beneath reality, but its greatest weakness is that the door may lead to questions we cannot actually test. A scientific idea becomes powerful when it does more than sound possible. It must help us tell the difference between one kind of world and another. It must give us some way, at least in principle, to discover whether it is wrong. This is one of the main problems with the simulation hypothesis. Many versions of it are so broad that almost any observation can fit inside them. If the universe looks smooth, the simulation is simply smooth. If the universe has limits, the simulation has limits. If physics is elegant, that elegance is called evidence of design. If physics is strange, that strangeness is also called evidence of design. When an idea can absorb every possible result, it becomes difficult to treat it as a scientific explanation. This does not mean the idea is foolish. It means it must be handled with great care. There is a difference between a meaningful possibility and a confirmed theory. A meaningful possibility can help us think. It can reveal assumptions. It can sharpen questions about mind, matter, and knowledge. But a confirmed scientific theory must be supported by evidence that could have turned out differently. It must stand in contact with measurement. At the moment, the simulation idea often remains closer to philosophy than established physics, because it does not yet give us a clear experimental signature that could separate a simulated universe from an unsimulated one. Another difficulty is that the word simulation carries a hidden picture inside it. We tend to imagine a computer, a programmer, a screen, and a world running inside some larger machine. But those images come from our own technology. They may be too human, too narrow, and too shaped by the present moment. A civilization far beyond ours, if such a civilization exists, might not use machines that resemble computers at all. Or the deeper foundation of reality, if there is one, might not be technological in any familiar sense. Calling it a simulation may be a metaphor rather than a literal description. Metaphors can be useful, but they can also mislead. When people say reality might be coded, they may imagine that natured from something like human software. But the laws of physics are not known to be instructions written in a language. They are patterns we discover and describe. The fact that the universe follows mathematical regularities does not automatically mean that someone wrote those regularities. Snowflakes have patterns. Crystals have symmetry. Planetary orbits can be described mathematically. None of this requires intention in the ordinary sense. Regularity is not the same as artificiality. There is also the problem of explanation. If our universe is simulated, then something outside our universe must support the simulation. But that larger reality would need its own explanation. What is it made of? Why does it have laws? How did it begin, if it began at all? Why does it permit the existence of the beings or processes that created our world? The simulation idea may answer one question only by moving it upward. Instead of asking why this universe exists, we ask why the universe containing the simulation exists. The mystery does not disappear. It changes location. This creates the problem of infinite regress. If our world is simulated by a higher world, perhaps that higher world is also simulated by an even higher one. And perhaps that world is simulated too. The chain could continue without reaching a final foundation. Some people find this exciting, like mirrors reflecting mirrors. But scientifically, it can become empty unless the chain eventually connects to something we can describe, test, or understand. A stack of hidden worlds may be imaginative, but imagination alone cannot explain why there is any reality at all. The hypothesis also depends on uncertain assumptions about consciousness. A simulated world, in the strongest sense, would not merely contain moving images or mathematical models. It would contain beings who actually experience. But we do not yet know whether consciousness can arise in a non-biological system, or what exact physical conditions are required for subjective awareness. We know that conscious experience is deeply connected with the activity of living brains. We know that changes in brain function can change perception, memory, emotion, and identity. But knowing these connections is not the same as having a complete theory of why experience exists. This is a major gap. If consciousness requires specific biological processes, then a digital or artificial simulation might not contain inner experience, even if it behaved convincingly from the outside. If consciousness depends mainly on organization and information processing, then it might be possible in many different physical systems. Science has not settled this. Until it does, claims about conscious simulated beings remain speculative. The simulation idea often assumes that minds can be generated by computation, but that assumption is one of the very things still being debated. There is also the question of scale. Simulating a universe like ours would be an enormous task, at least if it required tracking every particle, every field, every interaction, and every possible quantum detail. Some versions of the idea avoid this by suggesting that only what is observed needs to be fully resolved. But this suggestion raises further problems. In our universe, unobserved processes still leave traces. Distant stars evolve for billions of years before anyone studies their light. Geological layers record ancient events. Particles interact in hidden places and later affect visible outcomes. The world has deep consistency across space and time. Any simulation that produced this would need to preserve a vast web of causal structure. Perhaps an advanced system could do that, but saying perhaps is not the same as showing how. Our current technology gives us only a tiny analogy. We can simulate limited systems under simplified rules. We cannot simulate consciousness, a whole biosphere, a galaxy, or a complete quantum universe in the relevant sense. The simulation hypothesis often leans on future possibility, but future possibility is hard to measure. Many things are imaginable that may not be physically achievable. The universe may impose limits on computation, energy, memory, and information that no civilization can overcome. Probability arguments create another problem. Some versions of the hypothesis suggest that if advanced civilizations can create many simulated worlds, then simulated observers might vastly outnumber original observers. Therefore, we might be more likely to be simulated. The reasoning is interesting, but it depends on numbers we do not know. We do not know how many civilizations exist. We do not know how many survive long enough to become extremely advanced. We do not know whether they would create ancestor simulations. We do not know whether simulated minds are possible. We do not know how many would be created, or whether ethical constraints would prevent their creation. If the inputs are unknown, the probability can feel precise while resting on uncertainty. This is one of the dangers of the simulation idea. It can sound mathematical while depending on fragile assumptions. A chain of reasoning can be logically valid, yet still not tell us much about the real universe if its starting points are unknown. Science is full of careful probability, but good probability requires grounded information. Without that grounding, numbers can create an illusion of certainty. There is also an emotional problem. The idea can be captivating because it gives mystery a shape. It suggests that the hidden layer beneath reality might be understandable in terms of technology, intelligence, or design. That can feel more satisfying than a universe that simply exists according to impersonal laws. But satisfaction is not evidence. Human beings naturally prefer stories with agents, purposes, and secret causes. We are pattern-seeking creatures. This helps us learn, but it can also make us overinterpret uncertainty. A strange universe does not necessarily imply a hidden designer. It may simply be strange because nature is deeper than intuition. At the same time, dismissing the idea too quickly would also be unscientific. The history of knowledge includes many ideas that once seemed absurd and later became serious. The Earth moves, time is relative, matter behaves quantum mechanically, empty space has physical properties. These truths were not obvious from everyday life. So the right response to the simulation hypothesis is not mockery. It is disciplined curiosity. We can ask what the idea would require. We can ask what evidence would support it. We can ask where it becomes unclear, where it becomes too flexible, and where it teaches us something, even if it is not true. The most valuable role of the simulation idea may be this. It reminds us that reality is not obligated to match human intuition. It may have layers we do not yet understand, but it also reminds us that wonder needs discipline. Not every deep question has an immediate scientific answer. Not every possibility becomes a theory. Not every mystery should be filled too quickly. So the problem with the simulation idea is not that it is impossible. The problem is that it is difficult to define clearly, difficult to test, and easy to stretch beyond evidence. It raises profound questions about consciousness, information, technology, and the foundations of physics, but it does not yet solve them. It asks us to imagine a deeper reality, while leaving that deeper reality unexplained. And perhaps that is where we can leave it for now, gently unresolved. A question does not have to become an answer tonight. The world around you can remain steady, whether it is fundamental or layered, simple or strange. You can let the mystery stay open, breathe into the quiet, and rest inside the reality that is present enough to hold you. Chapter 10. If reality is real enough. After all the questions about hidden code, deeper layers, and the possibility of simulation, the final mystery may be the gentlest one. If a world can be experienced, shared, studied, and cared about, in what sense would it not be real enough? The simulation idea can feel unsettling because it seems to threaten the ordinary weight of life. If reality were not fundamental, people may wonder whether anything would still matter. Would a sunrise become less beautiful? Would a memory become less meaningful? Would kindness, fear, grief, curiosity, or love somehow become false? These worries are understandable, but they may come from treating reality as an all-or-nothing category. In science and philosophy, reality is often more layered than that. Something can be emergent and still be real. Something can depend on deeper processes and still have genuine effects. Something can be made of parts, patterns, or information and still matter to the beings who live through it. Consider a wave moving across the sea. A wave is not a separate object in the way a stone is. It is a pattern of motion in water, shaped by wind, gravity, depth, and surrounding waves. It rises, travels, breaks, and disappears. If you ask what the wave is made of, the answer is water. But saying it is only water does not make the wave unreal. The wave has a shape. It carries energy. It can move a boat, erode a shore, or reflect moonlight. It exists as a pattern, not as an independent substance. Its reality is not weakened by being dependent. It is real as a wave. Much of the world is like this. A rainbow is not a solid arch placed in the sky. It is an optical pattern created when light interacts with droplets of water and reaches an observer from the right angle. Move, and the rainbow changes. Yet it is not imaginary. It can be photographed, predicted, explained, and shared from nearby perspectives. Its reality depends on light, water, geometry, and observation. It is relational, but not fake. The same is true of many familiar things. A melody is not found in a single note. It exists in the pattern across notes and time. A living body is not just a pile of atoms, but an organized process that maintains itself for a while. This is why the simulation question does not automatically erase meaning. If reality were built on a deeper layer, then stars, bodies, thoughts, and histories might be emergent rather than fundamental. But emergence is not illusion. The wetness of water emerges from molecules interacting in vast numbers. The life of a cell emerges from chemistry organized in astonishingly precise ways. The mind emerges from the activity of the nervous system and the body, although consciousness remains incompletely understood. In each case, the higher level is not fake simply because it depends on the lower level. It has its own patterns, causes, and consequences. Science often works by moving between levels. It explains the behavior of gases through molecules, but it still uses pressure and temperature because those concepts are real and useful at the scale where gases are studied. It explains life through chemistry, but biology is not replaced by chemistry. It explains thought through brain activity, but a promise, a memory, or a decision cannot be understood by listing atoms alone. Each level has its own language because each level has patterns that become visible only there. If our universe had a deeper informational or computational foundation, the world we experience could still be real at the level where experience occurs. The word real can mean several things. It can mean fundamental, as in something that exists at the deepest level. It can mean independent, as in something that does not depend on one person's imagination. It can mean causally effective, as in something that can influence what happens. It can mean experienced, as in something that is part of conscious life. These meanings overlap, but they are not identical. A dream is experienced but not usually shared in the same stable way as waking life. A mathematical object may be abstract but still describe physical patterns. A social institution is not a physical object like a rock, but it can change lives, shape behavior, and endure across generations. Reality is not one simple box. It is a network of ways things can exist, act, and be known. Waking reality has many features that make it robust. It resists individual wishes. It is shared with other observers. It follows stable laws. It leaves records. It allows prediction, correction, and learning. If you misunderstand something, the world can push back. If a theory fails, experiments can reveal that failure. This resistance is part of what makes science possible. Whatever reality is at the deepest level, the world we inhabit is not a private fantasy. It has structure beyond any one mind. It can surprise us, teach us, and constrain us. A simulated world, if it contained conscious beings and stable laws, would also have this kind of internal reality. Its inhabitants would still face consequences. Their choices would still change future states of their world. Their sciences would still discover patterns inside the system. Their memories would still form part of their lives. If they felt pain, the pain would be real to them. If they felt wonder, the wonder would be real to them. The foundation might be different from what they assumed, but the lived reality would not simply vanish. This does not mean that the foundation is irrelevant. If we discovered that reality had a deeper artificial layer, it would transform philosophy, science, and our understanding of existence. It would raise enormous questions about origin, purpose, ethics, consciousness, and the nature of the layer beyond our own. It would not be a small discovery, but it would not necessarily make everyday life meaningless. A book is made of paper and ink or of pixels on a screen, yet the story can still move a person. A song is pressure waves or electrical signals, yet the music can still be beautiful. The substrate matters, but it does not always exhaust the meaning of the pattern. In fact, the simulation hypothesis can teach a calm lesson, even if it is false. It reminds us that reality may be deeper than appearance. It asks us to separate confidence from certainty. It encourages humility about the limits of perception and theory. It reminds us that human beings are not outside the universe looking in from a perfect vantage point. We are inside it, made of it, using part of reality to study the whole. Every instrument, equation, and idea is part of the same universe it investigates. That is not a weakness. It is the strange beauty of science. Science does not require absolute access to ultimate reality before it begins. It starts with patterns that can be observed, measured, repeated, and corrected. It builds reliable knowledge from limited perspectives. It does not answer every final question, but it gives us a way to move carefully through mystery. Whether the universe is fundamental, emergent, informational, or something beyond current language, the scientific approach remains the same in spirit. Look closely, test patiently, doubt honestly, and revise when the world teaches something new. This attitude protects us from two opposite mistakes. One mistake is to close the door too quickly and assume that familiar reality must be the whole story. History shows that nature is often stranger than common sense. Space and time are not as simple as they feel. Matter is not as solid as it appears. Empty space is not mere emptiness. The other mistake is to open the door so widely that every strange idea seems equally likely. Wonder needs evidence. Mystery needs discipline. A calm mind can hold possibility without turning it into belief. So where does that leave us? With a question that remains open but no less meaningful. We do not know whether reality is simulated. We do not know whether simulation is even the right word for any deeper layer that might exist. We do not know whether consciousness could be produced in an artificial system, or whether spacetime emerges from information in a way that would make our ordinary categories feel too small. These unknowns are real. But the absence of final answers does not empty the present moment of value. You are here within a universe that behaves consistently enough for memory, science, and care to exist. You can notice light, sound, breathing, warmth, and the passage of time. You can ask impossible questions while still living an ordinary life. That combination is not a contradiction. It may be one of the most human things about us. We can wonder whether the world is ultimate while still being moved by the world as it appears. If reality is fundamental, then this moment is part of the deep structure of existence. If reality is emergent, then this moment is part of a pattern vast enough to produce awareness. If reality is simulated, then this moment is still happening from the inside, still carrying experience, still forming memory, still touching whatever it means to be conscious. In every case, the life being lived is not nothing. It belongs to the world that contains it. Perhaps real enough means this: a world is real enough when it can hold experience, consequence, relationship, and discovery. It is real enough when it can be questioned by minds that arise within it. It is real enough when it can make room for both uncertainty and tenderness. The deepest foundation may remain hidden, but the surface is not empty. It is where all known life unfolds. And so, as this journey ends, you do not have to decide whether the universe is code, matter, information, dream, or something no human language can yet name. You can let the question rest without closing it. The night is still here. The breath is still gentle. The world, whatever it ultimately is real enough to carry you softly into sleep. And now, my friend, we can let this strange question rest. Whether reality is fundamental, emergent, informational, simulated, or something beyond any language we have today, this moment is still here. The night is still quiet, your breath is still steady, and the universe, whatever its deepest nature may be, is real enough to carry you gently forward. If you are still awake, you can continue drifting with another quiet journey through science, space, and the mysteries of existence. But if sleep is already close, let the questions fade into the dark, let the day release its weight, and allow yourself to rest. Good night, my friend. Sweet dreams among the stars.